Well, good morning, everyone. Thanks for being here. Hope you're having a good start of this conference. Welcome to the first talk of the day. The topic here is structured concurrency in Java. The talk is actually divided in three parts. Part one, we have introduction to structured concurrency. Then we have part two, where we will see structured concurrency in Java. And then in part three, we will compare the structured concurrency API with CompletableFuture API with some examples. So that will be the plan. So let's get started. Before that, a quick intro about me. So I'm Balkrishna Rawool. I work for ING Bank as an engineering lead. And one more quick word. If you have any questions, you can go to this URL and you can ask your questions throughout the talk. And don't forget to select Cinema 5 so that your question ends up at the right place. Also, depending on the number of questions and depending on the number of time that we have at the end, I will try to answer as many questions as possible, but if there are still some questions left, you can ask them afterwards, after the talk, or during the conference. You can find me. I will be around. OK, so let's start with the first part, introduction to structured concurrency. And for that, let's go way back in time to early programs. Early programs where the only mechanism to control the control flow of the program was goto statements. Now, what you see here is a program with sequence of instructions. And then you could use goto, which were interspurts in the program. And the thing with goto was that if you had few of these goto statements, you could still understand what is going on in the program. You could still wrap your head around it. But if you have too many of them, your program becomes spaghetti. So the problem with gotos is that it is difficult to isolate a part of the program from the rest of the program. It adds high cognitive load, and it is difficult. It makes the programs difficult to read and difficult to understand. Now, in order to solve these problems, Edgar Dijkstra proposed structured programming. And structured programming introduced control structures like conditionals or loops and subroutines. So what they did was that they made programs easier to read and easier to understand, because by using these control flows, you can isolate part of the program, and that makes your programs easy to read. So structured programming, as proposed by Edgar Dijkstra, prohibited the use of goto, and it introduced control structures like conditionals, loops, and subroutines. And that made programs easier to read and easier to understand. So basically, the issues with goto were removed. Now let's come to the current times. Let's talk about modern concurrent programs. Now, modern concurrent programs also suffer from a similar problem. You have a main thread, and from there, you can create a bunch of subthreads. Right? So you can create more threads. And creating a new thread is like using goto. With goto, your control gets transferred, but when you create a new thread, your control gets split. Right? It continues in the same thread, but also continues in the new thread. So if you have too many of these threads, again, you have same problems as you had with goto. So basically, in modern programs, starting a new thread is like using goto. And multi-threaded concurrent programs have the same problems as the programs with gotos. Now, is there structured programming but for concurrent programs? Well, yes, there is. That is what structured concurrency is. In fact, the term structured concurrency is derived from the term structured programming. And what it does is it addresses these issues that we earlier discussed. And the principle here is that if a thread or a task is started in a scope, it has to join or cancel in the same scope. And it brings in structure and order to the concurrency aspect of programs, and it makes concurrent programs easier to read and easier to understand. Basically, the readability benefit that structured programming brought to programs, it is the same benefit that structured concurrency promises to bring, but for concurrent programs. So that is end of part one. And I will start part two, where we will look at structured concurrency in Java, so how it is achieved in Java. And for that, we have to look at Project Loom. Now, Project Loom is an important project at OpenJDK, and the purpose of Project Loom is to support easy-to-use, high-throughput, lightweight concurrency and programming models for it. So basically, concurrency is at the core of Project Loom, and the idea is to provide lightweight concurrency, one which is also easy to use and provides high throughput. And it does so by providing three features, which are mainly virtual threads, structured concurrency, and scoped values. Now, virtual threads are lightweight user threads. Structured concurrency, as we saw earlier, is basically now brings structure to the concurrency aspect of programs, and scoped values are there to solve specific problems with thread locals when dealing with virtual threads. And virtual threads are actually a final feature since Java 21, but structured concurrency and scoped values are still in preview as of Java 22. And the focus of this talk is structured concurrency, so we'll discuss that in detail. And for that, we'll also get a quick intro to virtual threads, but we'll not discuss scoped values. So for this talk, they are out of scope. Let's start with virtual threads, and for that, we have to discuss first platform threads. So platform threads are actually threads which are present in Java for a really long time, right? So they are a wrapper over operating system threads. So what that means is if a JVM instance wants to create a new platform thread, it requests operating system to create a new thread. And only when the operating system thread can be created, it creates an instance of a platform thread. What that means is there's actually one-to-one mapping between platform threads and operating system threads. So one instance of platform thread actually is mapped to one and exactly one instance of operating system thread. Also, they require pooling. So creating a platform thread is a resource-intensive task, and therefore you don't want to create too many of them. So what you do is you put them in a pool. So when you are done with a platform thread, you don't throw it away. You put it in a pool so that next time when you need it, you use it from the pool. Virtual thread, on the other hand, are lightweight user threads. Lightweight meaning they require significantly less memory. And because of that, you can create too many of them. You can create thousands or even millions of virtual threads, and that makes them highly scalable. There's actually one more property or feature of virtual threads which makes them scalable, and we'll see that in a few minutes. And another thing about virtual threads is that they don't need pooling, because creating a virtual thread is a pretty cheap operation. So when you're done with the virtual thread, you just throw it away, and when the next time you need it, you create a new one. So you don't really pool them. In fact, pooling virtual threads is an anti-pattern. You don't want to do that. Also, what you see here in the picture, you see a lot of virtual threads and very few platform threads. And some of these virtual threads are mapped to platform threads. And that is because a virtual thread on its own cannot execute anything. It requires platform thread to execute something, to do something. But what about these other virtual threads, which are not mapped to platform threads? Now, for them, we have virtual thread scheduler. So what this scheduler does is it mounts a virtual thread onto a platform thread when a virtual thread requires platform thread, and it unmounts the virtual thread from the platform thread when it does not require platform thread. Now, what would be the scenarios where a virtual thread would not require a platform thread? It would be when a thread is waiting for something. So for example, if a virtual thread is waiting for a network resource to be available or database to return something. So in all these cases, a virtual thread is waiting. It is not doing anything. It does not require platform thread. It does not require CPU. So it gets unmounted from the platform thread. And in a typical IO-bound application, you have a lot of threads waiting for quite some time, right? So if you use virtual threads, basically avoid all that waiting. So your platform threads are not waiting. So your threads and your CPU is utilized to the max, and that also makes your virtual threads highly scalable. Another thing, so in this entire endeavor where threads are being mounted and unmounted, the platform thread is carrying virtual thread, so it is also known as carrier thread. Okay, so we have seen a lot of theory about virtual threads. Now let's see them in action, and let's create some virtual threads. Okay, you are able to see IntelliJ. I hope the font is big enough. I have already increased it. Is it okay in the back? Yes, perfect. Okay, so let's first create some platform threads. And a straightforward way to create a new platform thread is just to do new thread and then pass runnable to it. So in this case, I just want to print the current thread. Let's do that, and let's start a new platform thread. Now, if I run this, now in order to run this, I actually have a JUnit test. Although it's not really a test, it's just a wrapper on this method, so it executes it. So if I run this, I will get a new instance of platform thread. Oh, here it is. Again, with Project Loom, we have a new API to create platform thread, and that would be thread.ofPlatform. So this method would give us a platform thread builder, and onto that we can call start, which would start a platform thread. So if I do this, it will do exactly the same thing, gives me a new platform thread. Okay, so if this is the way to create a platform thread, you can imagine an equivalent way to create a virtual thread. So you could do of virtual and this would give me a virtual thread builder. Then I can do start on it to create a virtual thread. So if I run that, I see a virtual thread here. Now, if you look at the two-string representation of the virtual thread, you can notice a couple of things. One is this part, which is actually the ID of the virtual thread, and this is unique for each virtual thread. Also, this part is actually the platform thread onto which this virtual thread was mounted on while it was executing the statement. Right? So you get some information about the platform thread as well. We also have a shorthand method, so you could simply do thread.start virtual thread, and this would start a new virtual thread. So if I run this, I again get a new virtual thread. And there's actually one more way. So you can also use executor service to create virtual thread. Let me do that. Try where executor start new virtual thread per task executor. So if I do this, this will give me an executor service, but that service will not be backed by a thread pool. Because when you request a new thread, this gives you an instance of virtual thread, and virtual threads are supposed to be pooled. So this just gives you a new instance of virtual thread each time you request it. And the way to do that is just call executor.submit and submit a task to it. So in this case, again, I'm just going to print the current thread. So this will create a new virtual thread. So if I run this, again, I see the same thing. I see a new virtual thread instance. I can actually create a bunch of these threads. So let's do that. And because I'm using try with resources, this will ensure that all these threads that are started are finished before I exit this try block. So now if I run this, I will see a bunch of virtual threads. Again, if you notice these IDs, they are all unique, meaning these are all different instances of virtual threads. But if you see here, a bunch of them are mapped to the same platform thread. So what is happening here is that you have this instance of virtual thread, which is mapped to this platform thread. And when it was done, it was unmounted, and a new virtual thread got mounted onto this same platform thread. So basically, we see that mounting and unmounting in action here. OK, so we have seen how to create a virtual thread, but how do you use it? Well, the best way to use a virtual thread is to model a single business task with it. With platform threads, we see that platform thread as an abstraction of a process that is running on CPU, and we submit multiple tasks to it. But with virtual threads, you can actually create a new virtual thread for each task. Because with platform threads, we have the limitation that we don't want to create too many of them, right? But that limitation is not there with virtual threads. So you can actually create a new virtual thread for each task. And the advantage is that then you can structure these tasks and structure these virtual threads in such a way that represents your requirements in the most logical way, right? And that is what structured concurrency is. So basically, virtual threads takes away that limitation that you don't want to create too many threads, and therefore we have that liberty to create a new thread for each task and then structure these in the most logical way. We'll see a few examples. So here you see a main task, which is starting 3 subtasks, and when all of these subtasks are finished, we continue with the main task. So when you use structured concurrency, you will create a new virtual thread for each of these tasks. Again, here you have a main task, which is starting 3 subtasks, and then you don't wait for all of them to be finished. When one of them is finished, you continue with the main task. Again, you can use structured concurrency here. And a bit more complicated example. So here you have a main task, which is starting 3 subtasks, and when tasks 2 and 3 are finished, you start with the 4th subtask. And then when 1 and 4 are finished, then you continue with your main task. Now, all of these examples can be implemented using structured concurrency. And more specifically, if you talk about Java, you can implement them using Structured Task Scope API. And we'll see that in a bit. A bit more about structured concurrency. So the principle is that when flow of execution splits into multiple concurrent flows, they rejoin in the same code block. For example, here, so again, the same example from the previous slide, you have a main task, 3 subtasks. When all of them are finished, you continue with your main task. Now, if you see the implementation of this using Structured Concurrency API, you will see that the forking and joining happens in the same code block. I will see that in a bit. So what are the advantages of doing that? The first advantage is that error handling with short circuiting. So here you want all the subtasks to be finished. Now what if one of them fails? In that case, there is no point in continuing with the other task, right? Because one fails, you don't want to do execution because anyways your entire operation is failed, right? So therefore, you immediately cancel these other tasks, and that is what short circuiting is. Another advantage, cancellation propagation. So here, if, let's say, your main task is cancelled. Now that cancellation is immediately propagated to the child tasks, and those are also cancelled. And that is what cancellation propagation is. Clarity. So if you see this structure, right, and if you implement this using Structured Concurrency API, this structure is reflected in your code. So that brings in a lot of clarity, and it makes your code easy to read, easy to understand. Observability. So here you have a main task, which is starting 3 child tasks. Now imagine each of these child tasks have their own child task, and them having their own child task. So you can basically have a big hierarchy of tasks. And because we create a virtual thread for each task, you will have a big hierarchy of virtual threads. Now, for some reason, if you wanna, you have some problem and you want to take a thread dump of that hierarchy, you can actually get that thread dump in a format that reflects that hierarchy. And then you can point to the specific virtual thread that has problem, and then you can fix the problem. So that is the benefit, that is one of the observability benefits that structured concurrency brings in. Okay, so this is the end of part 2, and now we'll start part 3, where we will compare the CompletableFuture API with Structured Concurrency API. What we will do is we have a few examples, and we will, for each example, we will first implement using CompletableFuture API, then using Structured Concurrency API, and then we will do comparison. But before that, let's take a quick look at CompletableFuture. So it provides a powerful API for asynchronous processing, and it allows us to chain multiple stages to create pipelines, and it does so by using callbacks. So let's start with the first example or first use case. It is called event management. So here you have 3 tasks: reserve venue, book hotel, buy supplies, and you want to finish all of these tasks before you continue and create your event object. So how do you implement this using CompletableFuture? Let me show that. Here, so I already have it implemented. Here what do we do is we create 3 completable futures, each of them performing these tasks: reserve venue, book hotel, buy supplies. And then we combine these futures by using CompletableFuture.allof. So what this does is it gives you a future which will be completed when all of these underlying futures are completed, right? That is what we want. Then we do some exception handling, then we use then apply to get the results of these futures, and then we create our event object. Let's see what is happening here in the event util. So here, basically, I have these 3 tasks, which do log and wait, and then return some dummy data. What happens inside log and wait? It waits for some random amount of time, but before waiting, it prints which thread it is executing, which task it is performing, how long it will take. Then it waits, and then after the wait, it says the task is done. And okay, in order to run this, again, I have JUnit test. So if it's a wrapper, not really a unit test. So let me run this and see what happens. So if I run this, I see that it started 3 platform threads. Each of them are executing these tasks, and they take some random amount of time. And when all of these tasks are done, I get my event object. So this is exactly what we wanted, right? Now, how do you implement this using Structured Concurrency API? Let's do that. So for that, we always start with try with resources, and we create a scope object, which is structured task scope. Okay, so structured task scope is auto-closable, and therefore we use it with try with resources. So basically, when you're done with it, it frees up some resources. And then structured task scope has 2 subclasses: shutdown on failure and shutdown on success. And in this case, because we want all the subtasks to be finished, right? We want reserve venue, book hotel, buy supplies. We want all of these things to be done. That's why we use shutdown on failure. So you use shutdown on failure when you want all of your subtasks to be finished. Now, why is it called shutdown on failure? Because if you want all of your subtasks to be finished, and if there is a failure in one of them, there is no point in continuing, right? So basically, you just stop at that point and say, hey, there is a failure. So it's called shutdown on failure. And then you fork your subtasks. So you do scope.fork and then fork these tasks. So first this one. And when you do scope.fork, it gives you a structured task scope subtask, an instance of subtask. Let's put that in task 1 and then create more tasks. So this is for book hotel, and this is for buying supplies. These will be task 2 and task 3. and then we can do scope.join. So this will ensure that all the tasks are finished because we are using shutdown on failure. Then we do some exception handling and then exception propagation. And now that we have ensured that all the tasks are finished, we can get the results. So we can do task1.get. So this will give you a venue. And we can do task2.get, task3.get, which will give you hotel and supplies. Okay, and then we can create event. Which will have venue, hotel, and supplies. And then we can print the event. So if I run this, what do I get? I get 3 virtual threads performing these 3 tasks and running for some random amount of time. And when all of them are done, I get my event object. So again, this is exactly what we wanted, and this works same way as the CompletableFuture implementation, with the only difference is that here it uses virtual threads instead of platform threads. So now that we have equivalent implementations, let's compare them. So if I compare, what I see is that CompletableFuture provides an API which makes use of callbacks, whereas Structured Concurrency provides a bit more imperative API. So what you do here is that you create new scope, you fork subtasks, then you join them, and then you get your result. Right? So it's pretty imperative. Also, CompletableFuture makes use of runtime exceptions. So it throws this completion exception, which is a runtime exception. And if you look at Structured Concurrency, it throws this execution exception, which is a checked exception. So you have to basically catch it and handle it. Another thing to mention is that this CompletableFuture.allof, this gives you an instance of CompletableFuture void. So you basically always end up having this argument which is never used. You could always replace it with underscore. I guess that's about it for the first example. Then let's move on to the second example, which is weather service. So here you have 3 sources where you get weather information from, and you're only interested in one of them being successful. Right? So once you have one successful response, you don't want to continue with the others because that's what you need. So how do you implement this with CompletableFuture? Let's go back and see. We have weather here. So here again, I have 3 completable futures, each of them getting weather information from each of the sources. And then I combine them using any of. Right? And what this does is it gives me a future which will be completed when any one of the futures are completed. Right? Then I do some exception handling, and then we use then except to get the result, and we print the result. Okay, so if I run this, let's see what happens. So this starts 3 platform threads, each of them getting weather from 3 sources, and source 2 finishes fast. It only takes 2 seconds. So we get the result from there, and the other 2 are ignored or cancelled. Right? So we get only information from source 2, which is here. Yeah, so this is exactly what we wanted. Now let's implement this using Structured Concurrency API. Again, we start with try with resources, and we create a scope object. And in this case, we want to use shutdown on success. And that is because we are only interested in one of the subtasks to be successful. Right? So in that case, you use shutdown on success. Why is it called shutdown on success? Because when you want one of the subtasks to be finished, and one of them finishes successfully, you can stop. You don't want to continue because you have one successful completion, and that's enough. Right? So that's why it's called shutdown on success. And here it also takes a type parameter. So this is basically type of the result, and in this case it is weather. So I'm just gonna put weather here, and then go ahead and fork subtasks. So I do scope.fork, and then use the subtask, which is basically get weather from one of these sources. So this is 1. Then I have source 2, and then source 3. Okay, then I can join them. So what this will do is this will ensure that one of the subtasks are finished. And let me do exception handling. And in case of shutdown on success, you can directly get the result here. So if I do dot result and do the exception handling, and then basically it gives me weather, and I can put that in variable weather, and then print that out. So if I run this, let's see what happens. What it does, it creates 3 virtual threads, and they are performing, getting the information from each of these sources. In this case, source 1 is the fastest, so we get the weather from source 1. The other 2 are cancelled, and then we have this weather information here. Again, so this is exactly same as the CompletableFuture counterpart. The only difference is that here it uses virtual threads instead of platform threads. Now let's compare them. If I compare, again, we have similar differences. So you have the callbacks versus imperative API. You have runtime exceptions versus checked exceptions. And also one more thing, for example, this any of here, it gives me a completable feature of object. Although all the underlying features are features of weather, but I get the result which is completable feature of object. So this weather here is actually an instance of object. The type information is lost here. But in case of structured concurrency, the result that I get is weather is a weather instance. So it retains the type information. Okay, now I have a question for you. So here in this example where we have these 3 completable features, let's say one of them fails and fails immediately. So it throws new runtime exception. But the other 2 tasks can continue and can give you successful response. And then we combine these features using any of. So we have a situation where we have 3 features. One of them fails immediately. The other 2 can continue and give successful response. And if we combine them using any of, what do you think will happen? Now, the resulting feature, will it throw a runtime exception, or will it actually give successful response? How many of you think it will give an exception? Okay, quite a few. So like 50% of you think that. Now let's run this and see. It actually throws a runtime exception. Although we are saying that we are interested in any of the results, what it does is actually stops the first time it gets a completion of a feature. Whether it is successful or failure doesn't matter. And in this case, unfortunately, it is a failure, so we get a runtime exception. Now let's execute the exactly same thing with structured concurrency, and let's run this. Now, how many of you think there will be an error? Okay, none. Let's run this. It is a structured concurrency talk, so probably we have success. Well, it is a success. So it ignores the error, and I think this is a bit logical. In my opinion, this is more logical than the CompletableFuture implementation, because we're interested in one of them succeeding, right? So if there is a failure, ignore that and still wait for a successful result. And I got asked question about what happens to the error. Can we get still access to the error? Yes, we can. So if you extend this shutdown on success, and then you get access to your error and you can do anything with it. But in this case, again, it is a bit more logical than the CompletableFuture implementation. However, I think CompletableFuture, it is also okay if you throw an error. But then you need to know this is exactly how CompletableFuture.any works, and then if you can manage that, it is still fine. Okay, so that's a second use case. Now, third use case here, it is a bit more complicated. So here the first task we have is to get customer data. It is called banking portal. So the first task is getting customer data. And once you have customer data, you start these 2 tasks. Again, they execute at the same time. And here you get savings data and loans data. And when both these tasks are finished, you have everything that is needed to create offer. So you do calculate offer, which gives you an offer instance. And then you use that, continue with your main task. Okay, how do you implement this with CompletableFuture? And I have it already implemented here. So I have a first CompletableFuture, which gets the current customer. And then I create 2 more features, each of them performing get savings data and get loans data. And they are created by apply async on the first feature. So basically, we ensure that these 2 run concurrently. Then we wait for the response of the first feature, which gives us customer. Then we combine feature 2 and feature 3 to create customer details. And then we use that to do calculate offer, some exception handling. And finally, we have our offer. So let's run this and see if it actually works in the way we want. So we have get offer for customer. And if I run this, I have first a platform thread executing get current customer. Once that is done, I have 2 more threads performing these 2 tasks. And when both of them are done, I have final thread performing this calculate offer, which gives me an offer. So again, this is exactly what we wanted. So our implementation is okay. Now let's see how does the equivalent structured concurrency implementation looks like. Again, like we have been doing before, you could start with try with resources, right? So you do new scope with new structured task scope. But hang on, if you look at the implementation or the structure here, there's only one task to get customer data. So it's not like you have multiple tasks and you want to wait for all of them or one of them. So there is no need for a scope. There is no need for structured task scope. There's only one task. So we don't really need this here. But again, this is a blocking call, right? We are waiting for some other thing to give us customer data. So you don't want to do it in a platform thread. You want to do it in virtual thread so that our platform thread doesn't get blocked. So let's do that. Let's start a new virtual thread and make this call. So this will give us customer, which will be customer util dot get current customer. Okay, so this ensures that we have a virtual thread and we are executing this blocking call, and therefore this will not block the platform thread because we are in a virtual thread. Now let's imagine you have this application which is deployed on a server which is creating virtual threads for each request. So you are already executing in a virtual thread context, right? In that case, you don't really need a new virtual thread. So we can remove this as long as you are running on a server which is creating virtual threads. So then we can simply do this. But we are not deployed on a server, so what I've done is to simulate that environment that I have virtual threads. In my unit test, I'm starting a virtual thread. So this basically simulates that you have a server which is starting virtual threads and executing your logic. So basically this executes in a virtual thread, and therefore I can simply call this. So here we have a blocking call, but because we are operating in a virtual thread, we just call it as if it is non-blocking. So this feels a bit more liberating because you have blocking operation without any ceremony around it. And that is the power of virtual threads. Okay, so we have our customer. What do we do then? We have to now get the savings and loans data. And these two things happen at the same time. We want to wait for both of them. So let's use scope. So let's try with resources, create a scope instance, which will be structured task scope. And here we want to wait for both of them. So what do we use? Should we use shutdown on success or shutdown on failure? Failure? Yeah? Yes. So we use shutdown on failure. And then we fork our subtasks. So which would be basically customer util dot get savings data. Let's pass customer to it. And this gives a subtask. So let's put that in task 1. And then get loans data, put it in task 2. And then wait for them to be finished. And then exception propagation. Okay, and now that we have ensured both of them are finished, let's get the results. So we do task1.get, which gives us savings data. And then we do task2.get, which gives us loans data. And then we can create a customer details object, which will have customer, savings, and loans information. And once we have this, then we can go ahead and do the calculate offer. Now here again we have only one task, so there are no multiple tasks. There is no need for structured task scope or anything like that. But if there were multiple tasks, what you could do is you could create a new scope here. So you could do where scope 2, right? And use structured task scope and things like that. So basically you can nest your scope, and that is still fine. Right? Then you can basically do forking of subtasks using the scope 2 here. Or you could also reuse the same scope. So here you have a scope which you use to fork your subtasks. Then you join these subtasks. Now it is available again. So you could simply do scope.fork and fork new subtasks from it. So once you have a scope, you can fork subtasks, you can join them, and then you can reuse it again to fork subtasks and join them. But in this case, there is no need for a scope. We only have a single task, and we are operating in a virtual thread context, so we could simply call that. So we do customer detail dot calculate offer, and then we pass customer details to it, and this gives us an offer. And then we can simply print the offer. So if I run this, this will give me an offer, and let's run this. So we have one virtual thread which is running get current customer, which will finish in 5 seconds. After that, we have 2 more virtual threads running these 2 tasks parallelly. And once both of them are finished, then we do calculate offer, which gives us an offer. So again, this is same as the CompletableFuture implementation. The only difference is this uses virtual threads. Now let's compare these 2 implementations. Again, besides the obvious differences of callbacks and imperative API, runtime versus checked exceptions, what I see is that now this is the structure that we started with, and this is the structure that we wanted to be implemented. And that structure is not really evident from the CompletableFuture implementation. But if you look at the structured concurrency implementation, we see that we first get the customer, then we have a scope which is performing these 2 tasks at the same time, and when we have their results, we do this task. So basically, this structure is more evident in the structured concurrency implementation than the CompletableFuture implementation. Anything else? So we mentioned few of the advantages of using Structured Concurrency API. Are there any shortcomings? Well, at least there is one that I can mention. So let's go to this example with the event management. And if you look at all these examples, right, you have this pattern which is emerging again and again. So you first create a scope object, then you fork your subtasks, then you join them, and then you get the results. But this structure is not really, or this pattern is not really enforced at compile time. If I forget to do join, right, then the compiler is fine with it. And if I run this, let's see. Oh wait, I have some compiler error because of the catch part. So again, here now compiler is fine with that. Let me show that. Yes. And if I run this, I get a runtime exception because I forgot to do join. But this could have been a compile time error rather than a runtime error. And there are a couple of such scenarios where you get runtime exceptions, which could have been compile time error. Okay, I think that's all I had to show about this. So let's continue with our presentation. Shutdown policies. So I did mention about shutdown on failure and shutdown on success. So you use shutdown on failure when you want all the subtasks to be finished, and shutdown on success when you want one of them to be finished. But what if you want something different than that? You have subtasks where you want a combination of these tasks to be finished, and the others are optional. You can create your own shutdown policy as well by extending structured task scope. So if you want custom shutdown policy, you extend structured task scope, and then you override handle complete method to provide your implementation there. And one last thing, and that is to be aware of pinning. And pinning is not really a structured concurrency phenomenon, but it is more a virtual thread thing. So what is pinning? Pinning is when a virtual thread cannot be unmounted from the platform thread. So virtual thread gets pinned to the platform thread. So when does it happen? It happens when virtual thread is executing a synchronized code block or a synchronized method, or if there is a native call. And you can detect that, you can identify pin threads by using JFR, JDK flight recorder. And in case of synchronized, it is actually only a problem if you are doing long running or blocking calls from the synchronized code block or method. But if you're not doing that, it is not that big of a problem because pinning happens for a really small amount of time and your application won't notice it. But if it is a problem, you can use, replace the synchronized code block or synchronized method with reentrant lock, and then it should be fine. And there is work going on to basically not let the virtual thread pin to the platform thread while executing a synchronized code block or method. So in future, we would, or like very recent future, you would see that synchronized code block or method is not really pinning your virtual thread. And that is all I had to share with you. So if you're interested in the source code, you can find it here on this QR code. If you have any questions, you can reach out to me on Twitter with that handle. And that is all I had to share with you. So thank you for being here and listening. Let's see if we have time for questions. Okay, we do have time, and we do have some questions. I showed the Slido thing at the beginning. Let's see if there are any questions. Oh yeah, I have a couple of questions, and I think I have the Slido app here. Yes. If virtual threads are mounted on platform threads, aren't the platform threads a bottleneck again? Well, the idea is that the idea is about waiting, right? So what happens is that virtual threads are mounted on platform threads, but during waiting, if there was no virtual thread, your platform thread would wait, right? It would get blocked as well. But when virtual thread gets blocked, it gets unmounted. So your platform thread is ready so that it can mount some other virtual threads. So then they are not the bottleneck anymore. I hope that answers your question. Is it possible to start virtual threads via CompletableFuture API? Well, I mean, it's just like any other API, right? So you can start your virtual thread from CompletableFuture, but do you really want to do that? I would say not, because I think with virtual threads, you have a nice API of structured concurrency. Let's use that instead of CompletableFuture API. And then the last question, is it possible to control amount of platform threads that will be used to mount virtual threads within structured task scope? Well, so basically controlling the amount of platform threads is not something you really want to do, because you only want to interact with the virtual threads API. But yes, there is a way to control the amount of platform threads. So when your JVM starts, you can submit a parameter to specify the number of platform threads. So actually, it uses fork join pool, a dedicated fork join pool specifically meant for virtual threads. And the default number of platform threads there is the number of CPU cores that you have. But you can change that by passing a JVM argument.